right. So now we're going to be live streaming in a second, and then I need to the other side mute it. People are showing up. Takes 30 seconds delay. Okay, that's why. Okay, now I delete it. All righty. I'm going to share. You can see the presentation, right? And then I think the participants, I don't know if Matthias usually shows up later. Okay. All right. So let me start with everybody. I think people are getting used to it again. I'd like to welcome back everybody to the SPICE-SPIN+X seminar series that we organize here in the Spin Phenomenon Interdisciplinary Center together with the Collaborative Research Center SPIN+X that is led by Martin Schliemann and Burger Hillebrands in Kaiserslautern and Matthias Kolowe here in Mainz. And here in the SPICE Center, we have myself, Harsinova, Angela Wittmann, and Karen Everso-Sete as scientific coordinators. As you know, this is a Zoom webinar format with always at 3 p.m. We have every Wednesday now. We can start it again in the fall. This is the beginning of our semester. The seminar, so please check out the next few talks that will happen in the next sessions. And if you have questions, please write them on your Q&A or raise your hands afterwards. Today, the speaker is Arnab Bose. I hope I pronounce it. Or is it Bose or Bose? I'm not sure.
Both are okay.
Both are okay. So he's a very talented young scientist that started at the IIT in Bombay doing his PhD, and joined Cornell University, the very high top team of Dan Ralph, looking at the spin phenomena, particularly at the altermagnets, the new class of magnetic materials that have shown to exhibit broken time versus symmetry momentum space, and showing some very interesting effects that they immediately followed up the prediction and will tell us all about it, about the observations. So with that, I'm going to stop sharing, and I'm going to ask Arnab to go, please, to share your slides and begin the talk whenever you are ready. And, okay.
Are you able to see my presentation?
We see the presentation, yeah. So go ahead whenever you're ready.
Okay. Thank you so much. Thanks for this nice introduction. And it is a great honor for me to discuss our recent research works in this platform. Today, I'll talk about the generation of electric field-induced unconventional spin current. This work was done when I was doing postdoc at Cornell University. Today, I'll talk about two different aspects. One is the tilted spin current generated by ruthenium dioxide. And then if time permits, I'll talk about the spin burst effect. So in the ruthenium dioxide, basically, we are reporting spin orbit torques in ruthenium dioxide permalloy bilayers. So first I'll start discussing the measurement techniques, followed by the spin split bands that could generate such unconventional spin current. And then I'll talk about our experimental results, mainly highlighting the crystal axis dependence of the unconventional tilted spin current. And in the next part of my talk, I'll discuss the thermal generation of spin current and the experimental techniques. And basically, we will be measuring the Hall voltage by applying either electric current or thermal gradient. By comparing the ratios of the electric and thermally driven Hall voltage, we can exactly identify what are the origins of thermally driven spin current. Okay, so let's get started with this first part, which is related to the generation of tilted spin current by altermagnet ruthenium dioxide. So let's start with the background of spin orbit torques. For the spin orbit torque, we need a source of spin current. And spin Hall effect is one of the phenomena by which we can get transverse spin current when longitudinal electric current is applied in a heavy metal. The generated spins are orthogonal to both the flow of the electric current and the flow of the spin current. Now, if we have an adjacent magnet, the magnet absorbs the spin current and it experiences different types of torques, damping-like torque and field-like torques. Now, if the spin current density is enough, eventually it can switch this magnet and we can read the magnetization state by measuring TMR of an MTJ fabricated on top of the heavy metal, which has been reported in this pioneer work. So not only the in-plane magnet, the spin orbit torque can also be useful to manipulate the outer plane magnet. But for the outer plane magnet, it is not very efficient for the deterministic switching because the accumulated spins are orthogonal to the magnetization. But we can always make some tricks, such as by applying external field, we can tilt the magnetization a bit. And on top of that, spin orbit torque can be activated and it can switch, as reported in these pioneer works. In this case, we can read out the magnetization state by measuring the anomalous Hall voltage. So this is very interesting and quite motivating. This is particularly interesting for the high density memory application. But we see that this is not very ideal situation because we need to apply symmetry breaking field in most of the cases. So however, we would ideally need a material where by applying in-plane current, we can get out-of-plane spins flowing in the out-of-plane direction, which will immediately cause the out-of-plane anti-damping torque on the adjacent PMA magnet. I refer this unconventional out-of-plane damping-like torques. Now, naturally, the question arises in which materials we expect such thing to happen. So now let's assume we have a material, and when we apply in-plane electric current, let's assume that it generates out-of-plane spins. Now, by taking the mirrored inversion, we see that the polarity of the accumulated spins flip, but not the electric current. That means it will not be allowed in most of the polycrystalline materials. But however, if you break the mirrored symmetry perpendicular to the direction of the applied current, this would be allowed, as reported for the first time in tungsten titelluride and also recently different type of single crystal materials. But this is not the only way we can break the symmetry. However, if we have magnetic ordering, that also breaks the symmetry, and we can also obtain different type of unconventional torques. More details can be found in this review article. However, for now, I'll give you two instances. In this case, we have magnetic trilayers, out-of-plane iron cobalt boron and in-plane permalloy. We have a spacer in between. In this work, it has been reported that by applying in-plane current, one can get out-of-plane spins, which will produce out-of-plane anti-damping torque. In one of my previous works, I have also studied spin torques in the in-plane GMR, with one magnet is free, another magnet was fixed. By applying in-plane current, I observed that it generates an effective out-of-plane magnetic field. So both of those are efficient to manipulate the PMA magnet. But however, there could be some issues issues of ferromagnet as a source of such unconventional torques, because the magnetization can be influenced by external field perturbation. So we may need robustness like a heavy metal and at the same time magnetic ordering. So simultaneously it can be fulfilled if we have an anti-ferromagnet, which I'll discuss in the next part of my talk. So now let's have a look what are the different types of spin current and spin torques we can get from a system and how do we experimentally measure it. So these are the three possibilities. In all the cases, we apply in-plane current and spins flow out of the plane from the generator to the adjacent magnet. So first one is very known to us, that is a spin Hall effect or Roche-Bedelstein effect, where the accumulated spins are orthogonal to the direction of the applied current. We can also have situation where the generated spins are polarized along the direction of the applied electric field. Such things happen in materials having exhibiting Dresselhaus-like interaction. In some materials where we have lower symmetry, sometimes that can also allow us to have out-of-plane spins flowing in the out-of-plane direction. Now, when we have spin current, they will interact with the adjacent magnet, and it can produce 6 different types of torques, 3 different types of damping-like torques, and 3 different types of field-like torques. So now these torques are very useful to manipulate the magnetization state and vice versa. Meaning, if we know the spin torque response in a system, from that we can know what type of spin current is generated. So that would be very useful. So to understand or to quantify the spin torques, experimentally, there are 2 techniques, in-plane second harmonic Hall and spin torque ferromagnetic resonance. So in this technique, we have bilayer consisting of a ferromagnet and the source of spin current. Now we run low frequency current in the system. And because of various current induced torques, there are various current induced torques on the magnet, and magnet oscillates both out of the plane and in the plane, resulting oscillatory magnetic resistance from anomalous Hall effect and planar Hall effect. Meaning we have alternating current and alternating resistance, and they mix up together to produce second harmonic Hall voltage. That is what we experimentally measure. And by fitting Hall voltage with these expressions, so we can identify and quantify all 6 different types of torques, because there are 6 parameters to fit. So note that here we do the experiment for different magnitude of the field, and by changing the magnitude of the field, we get the dependence of this coefficient, and from that we can distinguish whether generated second harmonic Hall voltage is related to spin orbit torque or a thermal effect. STFMR is very similar to in-plane second harmonic Hall. In this case, instead of applying low frequency AC current, we apply radio frequency current in the system. Again, there are various current induced torque, which drives magnet into resonance. Its magnetic resistance changes due to AMR. Now we have homodyne mixture of the radio frequency current and radio frequency resistance, which together produce DC voltage that we experimentally measure. And we fit, because of the resonance, we get we can get the symmetric and anti-symmetric Lorentzian. With this, we fit the data. From symmetric Lorentzian, we get the in-plane torques, and from anti-symmetric Lorentzian, we get all about out-of-plane torques. Now we repeat the experiment by applying magnetic field at different angles phi with respect to the current flow direction to get the angular dependence of the symmetric and anti-symmetric Lorentzian. Now again, there are 6 terms and 6 unknowns, unknown types of torques. And by fitting the angular dependent symmetric and anti-symmetric Lorentzian, again, we can identify and quantify 6 different types of torques. So these 2 techniques we have used in our experiment. Now I'll discuss our results, but before that, let me talk about the band structure. First, let's consider a simple ferromagnet where we have non-zero magnetization. So due to the global exchange field, we have spin-split bands, majority and minority bands. This is pretty standard for a ferromagnet. Now let's consider a simple case of a collinear antiferromagnet with net magnetization 0. So we have equal population of upspin and downspin electrons, as shown with green and purple color balls. Now taking by space inversion and time reversal, we see the material is PT symmetric. And the Kramer's theorem guarantees that in this case, we'll have spin degenerate bands. So this is very standard for the classical collinear antiferromagnet. Now let's have a look what happens for ruthenium dioxide. So these green and purple color balls refer to the ruthenium atoms having up and down spins, and black color balls refer to the non-magnetic oxygen atoms. If we ignore these non-magnetic oxygen atoms, this looks like exactly this classical collinear antiferromagnet just now I discussed. But the moment the oxygen atoms are considered, immediately it breaks the PT symmetry and we have 90-degree rotational symmetry. Since the PT symmetry is broken, now it is allowed to have the spin split bands, even though the net magnetization is 0, as theoretically predicted in these papers. So it is a real antiferromagnet in the real space, and however, it exhibits spin split bands like a ferromagnet in the momentum space. That's why it has been referred to a new class of material referring as altermagnet. And we'll see from the predictions that this spin split bands will have tremendous influence in the electronic transport properties. For example, direction of the applied current with respect to the crystal axis, we can get a behavior of a ferromagnet from this altermagnet. For example, it can exhibit longitudinal spin polarized current and anomalous Hall effect, so on. The third possibility is that even if there is zero spin orbit coupling, still this material can produce transverse pure spin current, which is fundamentally different from the spin Hall effect, because for the spin Hall effect, the requirement is spin orbit coupling. Unlike this case, here the requirement is the spin split bands. And another difference is the generated spins are polarized along the direction of the Niels vector. So this is a theory prediction, and this is our experimental demonstration. Now, question is, how do we experimentally distinguish spin Hall effect and this novel spin current from ruthenium dioxide? So first, let's consider the crystal structure of this. Now, this shaded area is 001 plane. This shaded area is 101 plane. Niels vector points roughly along 001 direction. The theory suggests that if we run current along 010 direction, then we have spin current flowing in 100 direction, as shown here, with spins being parallel along the Niels vector, meaning 001 direction. Now you may wonder, this also happens in the regular spin Hall effect. Current flowing along X, spins are flowing along Y with spin polarization along Z. But there is a difference. For the spin Hall effect, spins flow in all the planes equally, as shown here, which is forbidden for ruthenium dioxide. For example, in this case, we cannot have the spin current flowing out of the plane, meaning we cannot have spin current flowing in the 001 axis, because it is prohibited, because Niels vector points in that direction. So this is fundamentally different from the regular spin Hall effect. But the question is, experimentally, how do we distinguish it? So we found that for the 001 plane, it is difficult to distinguish. But if you work on a different plane, which is 101, then we'll be able to distinguish it. For example, now this is the this is the 101 plane, and this shaded area is 001 plane. And we can do coordinate rotation and get from this configuration to this by taking rotation along y axis. And because of this rotation, we immediately find that the generated spins will be tilted. So this is something really different that should happen for ruthenium dioxide due to the spin split bands, which is different, distinctly different from the regular spin Hall effect. So this is what we want to experimentally detect. Now for this, we fabricated devices such that we can run currents along different crystallographic axes, as shown here. And we are doing both STFMR and second harmonic Hall measurements. So here, note that in this plane, the Niels vector is canted, meaning it has projection in the plane and out of the plane. So it can generate out of plane spins when we flow current along 010 direction. Now, if we run current along an arbitrary direction at an angle psi, then we further see the projection of the Niels vector along the current and perpendicular to it. Meaning we can have all the components of spin current, X, Y, and Z, but they will have a unique and crystallographic angular dependence. So that would be the hallmark feature of this material. Again, question, how do we detect it and detect such spin current? So previously I mentioned that we can get it from the spin torque response. So we need a ferromagnet adjacent to ruthenium dioxide. We have permalloy. So from the spin torque response, we'll know the types of spin current that is generated. So in summary, we find that in this material, Y-polarized spins will create damping-like torque, which is proportional to cos square psi. Z-polarized spin will create damping-like torque proportional to cos psi, and X-polarized spins will create damping-like torque proportional to sin 2 psi. So we want to experimentally see whether this happens or not. Okay, so one more thing before showing the experimental results. We also have done first principle calculations. So we find that there are two sources of spin current, time odd spin current and time even spin current. Both of them originate from the spin split bands. But the time odd spin current is an order of magnitude higher than the time even spin current. And second thing, we need to note that if we have a macron size devices, then if we have multiple domains, then the time odd spin current can cancel out. But however, if we have more than 10% unbalanced domains, still we can have substantial contribution from time odd spin current, because this is 10 times stronger than the time even spin current. And second thing is that in the expression, there is scattering parameter for the time odd spin current. And we find that if we change resistivity by a factor of 2, then that will result a strong change in the spin Hall conductivity. So this is something which we can also experimentally try to observe. Okay. So now let's move on to the experimental part. So here we are doing STFMR. Now I will show the results whenever we are running current along psi equal to 0 axis and psi equal to 90. Just to remind you, we are applying microwave current, measuring DC voltage by sweeping an external magnetic field at an angle phi. We measure the DC voltage, which is split using symmetric and antisymmetric Lorentzian. We repeat the same experiment for different values of phi to get the angular dependence of this symmetric and antisymmetric Lorentzian, from which we can quantify different types of torques. So this is a result when we run current along this direction, 0, 1, 0 axis. So already we see a clear distinct difference in the symmetric and antisymmetric Lorentzian, the angular dependence of S and A. The angular dependence of S can be fit using cos phi sin 2 phi, which is the standard spin Hall effect contribution. But for the antisymmetric component, on top of the Oersted field, we have an extra contribution resulting sin 2 phi angular dependence. That indicates that we have an extraordinary torques generated by the out of plane spins flowing in the out of plane direction. But whenever we do the experiment by running current in this crystallographic direction, we see the regular response of this symmetric and antisymmetric Lorentzian. Both can be fit using the standard spin Hall effect and standard Oersted field. So we have strong crystallographic direction dependence of this extraordinary torques. So we want to cross-check this, or we want to verify this by doing other experimental method, which is the intense second harmonic Hall measurement. Just to remind you, in this case, we apply low frequency current in the system and measure the Hall voltage by rotating in plane magnetic field. And we record the second harmonic Hall voltage as a function of phi. Again, we can clearly see the distinct difference in the angular dependence in these two cases. So for this case, when we run current along psi equal to 90, everything is trivial. We have contribution from the spin Hall effect, regular spin Hall effect, and Oersted field. But however, for this case, the difference in the signal is predominantly because of this cos 2 phi term. Again, suggesting that we have an extraordinary torques getting generated due to out of plane spins flowing in the out of plane direction. So summary is, by doing two independent measurement, we come to the same conclusion that in this ruthenium dioxide 101 plane, we have strong crystallographic axis dependent out of plane anti-damping torque. So now we repeat this experiment for different crystallographic directions as shown here, and this is a summary. We find that Y-polarized spins generating damping like torque, which follows cos square psi angular dependence, Z-polarized spins create damping-like torque, which is called psi dependent, and X-polarized spins create damping-like torque, which is proportional to sine to psi. So this is pretty much consistent with the theoretical argument, and this indeed implies that we have the tilted spin current generated by ruthenium dioxide, which is a consequence of this novel spin speed bands. So we have also seen a couple of recent reports studying spin torques in this ruthenium dioxide, and particularly in this paper, they have reproduced our experimental observations. So previously also there has been report of spin torques generated by another collinear antiferromagnet, manganese to gold, but this work is completely different from that, because here we observed that the generated spins are polarized roughly along the direction of the Niels vector, unlike this case. So the antiferromagnetic spin Hall effect or the tilted spin current we are reporting here, it is fundamentally different from this. Okay, so now we provide some other experimental evidence. For example, what if it is not related to antiferromagnetic ordering, something related to the crystal structure? So we checked it by comparing iridium dioxide and ruthenium dioxide, because they are isostructural, their crystal, lattice constants are very much same, and the quality of the sample and the strain, everything is very similar in iridium dioxide and ruthenium dioxide. But we do not observe any extraordinary torques in the same iridium dioxide plane, meaning the butyl crystal structure is not enough. We need the Niels vector, or we need the spin split bands. But however, iridium dioxide itself can be quite interesting because it also hosts Dirac nodal lines and shows anisotropic spin Hall effect, which we studied in this paper. You can refer to this for more details of iridium dioxide. We also studied other planes of ruthenium dioxide, such as 001 plane. In that plane, we do not observe any extraordinary torques, which is also consistent with the theory, because this is not also theoretically expected to see extraordinary torques in the 001 plane, meaning we have very strong crystal axis and crystal plane dependence of the torques. We have also studied the torques by having spacer between ruthenium dioxide and permalloy. We see the signal strength goes down, but still we can measure a detectable extraordinary torques, meaning the spin current is generating from the bulk bands, from the bulk of the ruthenium dioxide. And we also vary the thickness of ruthenium dioxide, and we find the spin torque efficiency increases and tends to saturate when the thickness is about 10 nanometer. So this is all consistent with the theoretical predictions. So finally, as I mentioned before, temperature dependence measurement could be an indication to know if we have any contribution from the time odd spin current. So we did temperature dependent out of plane anti-damping torque efficiency measurement. We find that in one of the crystal axes, we never observe any extraordinary torque, but in other crystallographic axis, we always observe it, and that strongly increases as we cool down. So it increases nearly by factor of 3, meaning 200% as the material is cooled down. So this suggests that we could have a strong contribution from the time odd spin current as well. So let's summarize all this together. In this work, we are claiming, so we are doing spin torque measurements in high quality MB grown ruthenium dioxide and permalloy bilayers. We observed tilted spin current, which is consistent with the theoretical predictions of the spin split bands of ruthenium dioxide. We keep it in our mind that both time even and time odd spin current can produce such tilted spin current wherever, when the time odd spin current is predicted to be an order of magnitude larger. And we find an indication of time odd spin current because we see substantial change or increase in the spin Hall conductivity as the resistivity of material decreased. So this is a summary of this work. So since I have time, so I will now discuss the other another aspect of spin current generation from a heavy metal by applying thermal gradient. So here I'm talking about the spin-Nernst effect, which is the thermal analog of spin Hall effect. We have seen that there are discoveries of a lot of different type of Hall effects that have enriched this field of condensed matter physics. Spin Hall effect is one of them, in which we get the transverse spin current by applying longitudinal electric current. By the same argument, the question is, if we have longitudinal thermal gradient, then the question, can we have the transverse spin current? And if it is so, then question is, how do we experimentally and unambiguously measure it? So we have recently done some work. So I will explain our recent report in this context. So now question is, what could be the mechanisms? So one of the mechanisms could be the energy dependent of, energy derivative of spin dependent scattering. Meaning even if there is no net flow of charge current, when we apply the thermal gradient, still we can imagine the flow of hot and cold electrons just above and below the Fermi energy level, but they're equal and opposite, resulting net current equal to 0. But they can still have different scattering, and meaning finally it can lead to a resultant net spin current. Meaning, as predicted in this recent work, if we have energy derivatives of regular spin Hall effect, we can get the thermal analog of it. And the second thing is that when we apply the thermal gradient, we get the local electric field due to the Seebeck effect. And that electric field also brings the system in the non-equilibrium, shifting the Fermi spheres. And that could naturally lead the generation of transverse spin current without any scattering mechanism. That means for this mechanism, if we have a material that has high spin Hall effect and large spin Seebeck large charge Seebeck coefficient, then we can also have very large transverse spin current. So towards the end of this talk, I would be able to convince which of these mechanisms are the dominant contributors. So our experimental detection mechanism is the following. We run both electric current and thermal gradient and measure Hall voltage and compare them. So while we measure the Hall voltage, by the way, we are measuring in TMIG heavy metal bilayers. Our heavy metals are either tungsten or platinum. We chose tungsten or platinum because they are the strong spin Hall source. So we rotate magnetic field in the plane and we sweep magnetic field out of the plane. When we rotate magnetic field in the plane, we get sinusoidal sin 2π angular dependence. That's why I call it PHE-like signal. And when we scan a magnetic field out of the plane, we get step in the resistance. So I call it an AHE-like signal. So when we create the thermal gradient, we do observe the similar sort of angular dependence in the thermally driven voltages. So thermal gradient is applied by running electric current in the lithographically patterned heater, which is electrically isolated from the heavy metal ferromagnet bilayers. So this will establish in-plane thermal gradient. So these signals are quite similar. Only a small difference is that for this case, we have an additional cos phi angular dependence that originates from the longitudinal spin Seebeck effect. From this, we can also know how much is the unintentional out-of-plane thermal gradient we have when we try to create an in-plane thermal gradient. Now we need to understand the origins. So one of the possible origin could be the electrically and thermally driven spin Hall magnetoresistance. Just to remind you what happens in SMR. So when electric current or electric field is applied in ferromagnetic insulated heavy metal bilayer, again, the electric field could be applied by applying electric current or by applying thermal gradient. We can get the transverse spin current. And depending on whether they're collinear with the magnetization or not, they can transduce back. to the inverse spin Hall voltage, and they are orthogonal, then they will scatter and don't contribute. So this will result in both longitudinal and transverse magnetoresistance. And indeed, the transverse magnetoresistance can mimic like a PHE signal, even if the magnet is insulated, and also it can mimic the AHE-like signal. Okay, so we find that if the origin is spin Hall effect and spin-Nernst effect, just doing some simple calculation, we find that if we take the ratios of this transverse magnetoresistance driven by electric current and thermal gradient, then it should be strictly equal to 1. This is something what we want to experimentally investigate. If this is not equal to 1, then there must be some other origins which we need to figure out. So, so we have to evaluate this parameter eta for a given temperature. We find that whenever we try to create in-plane thermal gradient, the local or average temperature of the sample increases because we heat up the sample. And the increase in temperature could be very substantial. It can be more than 100 degrees C. So that must be taken care in the calculation. So we also, that's why we measure the electrical magnetoresistance as a function of temperature. The local temperature of the device is obtained from the resistivity of the devices. And here I show the thermal voltage as a function of heater power, suggesting that as we increase more heater power, the thermal voltage increases, which is quite obvious. And this data shows that as we go away from the heater, the voltage signal goes down. That is also quite expected. So now we have all the data to analyze this parameter for a given temperature. So for TMIG tungsten, we find that the value of eta is very close to 1, suggesting the origin is spin Hall and spin-Nernst. But for TMIG platinum, this value is substantially different than 1, meaning there must be some extra contribution, and we need to know what it is. So for that, we measured the traditional SMR, electrical SMR, by measuring the longitudinal sample resistance while rotating the magnetic field out of the plane in XZ and YZ. So in XZ scan will give us an AMR contribution, which is a property of a conducting magnet, and YZ scan will give us the information about SMR, meaning we'll pick up the information for spin Hall effects. In both these cases, we find large oscillation in magnetoresistance for both the cases, meaning in the YZ scan, meaning we have spin Hall effect, very strong spin Hall effect generated by both tungsten and platinum. But for the TMIG platinum sample, we do observe the oscillation in magnetoresistance in the XC field scan as well, meaning we have a bit of conducting magnet at the interface, unlike the case TMIG tungsten. So we refer this proximatized magnets at the interface are the source of this substantial deviation of eta, which makes it different than 1. So this is also consistent from the Morse theorem. It suggests that we can quantify the transverse thermal power if we know the longitudinal and the transverse resistivities. So there are different factors as shown here. And if we take the ratios of them, there is no reason that for a material that must be equal to 1. So in many cases, it may not be equal to 1. Just to cross-check this, what happens in a regular standard sample, such as iron, cobalt, boron 1 nanometer perpendicular magnet we considered. We did electrical and thermal measurements. We found both HE and PHE in the electrical measurement, and we do observe the anomalous Nernst effect, but planar Nernst signal was very small. It indeed implies that the value of eta could be different than 1 if we have a conducting magnet. So that is the justification that we made, that the conducting or semiconducting proximatized magnet at the interface of TMIG and platinum could lead to substantial deviation from 1. So there is also a recent report studying this same effect in TMIG platinum in this particular work, where they have also reported the value of eta substantially different than 1, which is also in agreement with our experimental observation. So it was explained with the thermal spin drag mechanism. So let me explain what it is. So when we try to create in-plane thermal gradient, we naturally get some out-of-plane thermal gradient, which will inject out-of-plane spins. And while these spins are driven along the in-plane thermal gradient, they can deflect sideways, and that lead to a second-order Hall voltage. And that would be proportional to the both in-plane and out-of-plane thermal gradient. So it would be proportional to the square of the heater power. In our experiment, we find that this voltage signal is very much linear with the heater power, giving us an impression that our data cannot be explained with this mechanism. And secondly, I mentioned that we could also understand how much is the out-of-plane unintentional gradient from this cos phi angular dependence, which we get from this expression. We find that as we go away from the heater, particularly when it is more than 100 microns, the out-of-plane thermal gradient is quite negligible. But however, still even in that case, the value of eta is substantially different than 1, even when the out-of-plane thermal gradient is negligible. So again, this cannot explain. So again, it suggests that our data cannot be explained by the proposed thermal spin drag mechanism. So now let me summarize. So we report the unambiguous detection of spin-burst effect in TMIG tungsten, which results the value of eta very close to 1 within our experimental uncertainties. So we did the same experiment in TMIG platinum. In this case, we find that the value of eta is quite a bit different from 1. And so it suggests that we have an additional contribution, which may originate from the magnetic proximity effect at the interface, which we found in this experiment. We rule out the contribution of thermal spin drag in our experiment from these two data, where we see the linear power dependence and the evidence of strong, very large value of eta, even when the thermal out-of-plane unintentional gradient is close to 0. And in the last, we can quantify an important parameter by taking the ratios of spin Hall and spin-burst angle. This implies that if this ratio is equal to 1, that means there could be a universal electric field that will generate the transverse spin current, and it doesn't matter, or it should not matter, how that electric field is created, whether by applying electric current or by thermal gradient. So we analyze the data for TMIG tungsten because this system is quite clean, free from magnetic proximity effect in the temperature regime we worked. So we find that the value is very close to 1 within our experimental uncertainty, suggesting the strong contribution, intrinsic contribution from the spin Berry curvature of tungsten. And yeah. So, and also this suggests that there could be, we can have a material where spin Hall effect is large, and also we can get large Seebeck coefficients such as bismuth selenite. In that system, we can also get very large transverse spin current, as reported in our recent archive paper. So for more details, you can refer to this work. Now I conclude my talk by acknowledging my colleagues, my group members, people who have grown iridium dioxide and ruthenium dioxide thin films, Ding Fu and working with Professor Symbol. They have done DFT calculation, which really helped us in the understanding of the tilted spin current in ruthenium dioxide. I'm grateful to Ms. Sang, working with Professor Muller. She did the TM imaging of our single crystal samples. For the thermal experiments, we collaborated with Professor Caroline Frost and Jackson Bauer grew the samples. Also, I'm very much grateful to my colleagues at Cornell, Rakshit, who did the low temperature measurements of ruthenium dioxide and a lot of instrumentation my postdoc supervisors, Professor Dan Bulk and Professor Berman, my funding agencies, and the great Cornell nanofabrication facilities and CCMR. So thank you so much for your attention, and I'm happy to take questions.
Well, thank you very much. That was very nice, thorough, very good tailored experiments that you've done. So please, everybody has a question, raise your hand if you'd like to ask a question. I think, let me see, I think ask Kamila, let me make him join. Some of the panelists. 1 second, I think hopefully they will join. So Akshat Mishra, which, okay, it's not joining, maybe allowed to talk. So Akshat, can you probably unmute yourself and ask your question? Can you hear us? Not having, we cannot hear you at the moment. So let me ask.
Yeah.
Go ahead. We can hear you now. Go ahead.
Thank you, Arnab, for the amazing talk. It would be helpful for me if you could explain what exactly are these time odd and time even spin currents.
So you can think about time odd spin current in this manner. Suppose if you have a magnet, if you run any charge current in the magnet, you get the spin polarized current. And if you flip the magnetization, you get the opposite sign of spin current, meaning you can control the sign of the spin current by doing the time reversal operation. So that is possible in ruthenium dioxide, and that effect is very strong. And the way you can think about time even spin current is just having a regular spin current from the spin Hall material, just the way it happens in platinum.
Okay. Thank you very much.
Meaning just one more point, meaning in general antiferromagnets, by doing 180-degree rotation, it doesn't make sense because it goes back to the same state. But here in ruthenium dioxide, it will matter. If you flip everything by 180-degree, you will get opposite sign of the spin current.
Okay, I get it. Thank you very much.
Okay. Do we have any further questions from the audience? I have a question because you were talking about the nurse effects on the direct effects. Maybe I missed it. Did you try to connect this Osaka reciprocity in the different scenarios and check it or not?
So here, okay, let me go back to the last slide. Yes, so here what we found is that for TMIG tungsten, we found that whenever we applied thermal gradient, particularly in this case, it creates local electric field because of the Seebeck coefficient. And we find that that local electric field produces the spin current. And now it doesn't matter. I can apply the same amount of electric field just by applying electric current. So it would also lead to the same amount of spin current. That's what I mean in this case.
Okay.
But again, the numbers are slightly different. If it is 1, then it would exactly mean that, but we are very close to 1, but not exactly equal to 1. So the deviation could be due to the scattering effects.
Okay. And in relation to the spin splitter experiment, were you able to, do you have a mechanism in mind that how would you be able to switch the NL vector in order to test that this is the, I mean, right now it's suggestive that this is the origin, but it's not fully from that perspective.
Yes. Yes, that is a very, that we had in our mind, but we could not eventually do it. So yeah, that is a really good thing to check. One possibility could be having annealing the sample in presence of magnetic field during the growth. Something like that may help, but I'm not exactly sure exactly how to control the Niels vector.
I'm not sure if that would tell you, that would favor 180, 180 degree.
Yes.
Maybe coupled with a gradient or something. Okay. Very good. Do we have any further questions from the audience? there's not as popular still. That things clear that it's the beginning of the season. I have to send a few emails maybe to the whole gang, and maybe or from the other one. So so if not, I'd like to thank you again for a very nice talk on very nice results, very thorough and careful experiments, particularly showcasing ruthenium oxide, which is our workhorse alter magnet that we're very excited about, and showing many very positive things. And with that, I would like to remind everybody that next week, the same time at 3 p.m., we'll have our next talk. And to please remind people that we are started again. So, you know, I know that, but likely, unfortunately, there's a lot of seminars and things now that are live. We're no longer stuck at home, so that's probably one of the reasons. But with that, I'm going to stop the streaming in a second here for a second. Stand streaming. Okay.